Welcome back. So, today I will talk about in this technical seminar I will try to cover two different things, that is two different avenues to probe new physics, that is one through direct search for heavy neutral lepton, and the other one is indirect search, like search for CP violation beyond standard model in charm. So, one search is done at Belle II while I completed that while I am here, and the other one what I am doing at Belle II that I will be discussing. Okay. So, as I said, there are two compelling paths to Arnold's physics. The target of the talk is search for this HNL, which is a hypothetical particle that can naturally explain the neutrino masses and baryon asymmetry of the universe. And the other is CP violation in charm, which is a unique window into the flavor physics beyond the standard model, which is complementary searching CP violation K1 and D-meson sector, but they are down type quark sector, but it is up type quark sector, and the standard model expectation in this sector is quite small. So, it offers a clean way to search for new physics. So, this analysis I have done at Belle, and what I am doing in charm is at Belle II. So, okay, so since these two particles that I will be talking about, one is HNL, that is kind of long lived search, and the other one is charm, which is a standard model long lived particle. So, what I mean by long lived particle? So, a particle can be detector prompt. What it means that it will decay immediately, we cannot measure the decay vertex, and it can be detected stable, that it passes all through the detector like pion and muon, or it is completely stable like electron. So, in the middle here we have the so called long lived particle. When I say long lived particle, that means it is long lived enough we can measure its decay vertex or flight distance, and at the same time it is short lived because we can see the decay vertex inside our detector, or we can see it decaying. So, that is what I mean by long lived here. So, these are all the standard model long lived particles that can be measured in the detector, and heavy neutral lepton that can be sourced, that is not beyond the standard model. Okay, so the heavy neutral lepton, what starts with the problem with the neutrino masses. We know the standard model has only left handed and that is massless neutrino, but we have observed that neutrino flavor oscillate, that is a super Mikunda experiment result, that muon neutrino coming far travels a long distance and gradually disappears as it goes to long distance divided over energy. So, it is disappearing to electron and tau neutrino, that we can see between the difference what is expected here. So, from different experiments we know that there is absolute limit on the neutrino masses because of the neutrino oscillation. What has been measured is the sum of neutrino masses to be less than 0.9 electron volt. So, how do we generate the neutrino masses? That is the question. So, there is a mechanism behind it, we call it seesaw mechanism. So, which takes into account this neutrino minimal standard model, where we have right handed neutrino along with the left handed standard model neutrino. So, in the Dirac we can write the Dirac Lagrangian and the Majorana Lagrangian and do diagonalization, and we end up with the these mass eigenstates, the mass of the light neutrino, which is square of the Dirac mass over the mass of Majorana mass, and the heavy neutral lepton, which is mostly the Majorana. So, that is why the seesaw mechanism, one is heavy, another is light, and so if the Dirac Majorana mass is something order of GeV, then Dirac mass. So, if Dirac mass is very small, then we can end up with somewhere here, and okay. So, the heavy neutral lepton is mostly the Majorana mass. Okay, so it will allow us to solve some of the outstanding problems on the standard model, like origin of the standard model neutrino masses, as I said, and the dark matter. For example, the possibility that there are three heavy neutral leptons, and the lightest one being in keV scale, it is the stable one, that is the dark matter candidate, and it can explain the matter antimatter asymmetry via leptogenesis, and it interacts with the standard model neutrino through mixing. And as an experimentalist, we will try to look for mass HNL in the GeV range, which actually presents for opportunity for interesting studies. So, Yeah.
Scale explains leptogenesis.
What mass?
Any mass scale it can explain.
So we can, if we look at here, like I am constraining GeV mass scale.
Okay. And at that scale, leptogenesis is what?
I think so, but I don't have one detailed idea. So, yeah, so generally we look for GeV scale and try to address that. I have to look at it. Yeah. Okay, so just to summarize, the mass eigenstate can be written as a linear combination of these flavor eigenstates, where the standard model neutrino is mostly left-handed with a small component from the right-handed neutrino, whereas the heavy neutral lepton is mostly right-handed with a small mixture from the left-handed component. And so the N can undergo standard model interaction just like just like left-handed neutrino, but it will be suppressed by a factor V. And this N can be produced in various ways. It can be produced from the G decay or W decay or lepton decay. So at LSE, I guess it's from QQ bar, so it can be from W or G. And what I will be focusing today, it's from the lepton decay, like tau lepton decay, and even from B decay, which is mediated by W. That is also possible. Belle has done it, but it's a different story. And what I am focusing is the tau lepton decay. And tau, the HNL produced from the tau lepton, and how it decays is through either through the charged current or neutral current process. So this is the way the HNL can decay through charged current process, and this is the way it can go through neutral current process. If it is a neutral current process, then in the final state we can have we can get a vertex out of two leptons, or I mean, if it is two quarks, it can be a charged pion or charged hadron, and also it can go to two neutrino final state. But given that the two neutrino final state, or the I mean, for example, charged pions, it's difficult to find the decay vertex. So I just focused on the two lepton final state. So this is the
So why you want to do the invisible search using electron?
it's possible.
You can even probe a larger values of V, because it's a long life.
But that will be very difficult, no? So you see, we have three neutrinos in the final state. So how will handle?
But in principle, if you extend.
Yeah, but like experimentally, it's far difficult. It's a tau and three neutrinos in the final state. In the background is searching for something in impossible. We are trying to search something that's clean.
But even then, no, I agree with whatever you're saying. But technically, since this heavy HNL mass is different, so if you are searching, if you are reconstructing the muon energy spectrum, that's very different. So there is some, in principle, there is something.
Yeah, it's possible, but you see, there are three neutrinos here. So tau, for example, goes to n pi or n lepton. Then again another more neutrino. Yeah. And then what will identify, recoil against what?
This is much more robust, I agree.
Yeah. No, not about this one. I mean, the one with many neutrinos in final state, it will be very challenging.
Okay, we can talk later. No, I'm saying I agree with whatever you're saying. It's challenging. But in principle, the advantage is that you can probe larger.
Yes, definitely. Yes. People do those searches, like in gamma final state, I think Babar has done. They look at things in the recoil mass of gamma. So there is an analysis, but that's not a displaced vortex analysis. What I am focusing is measuring the displaced vortex. Yeah, so that's kind of prompt analysis. Yeah.
How do you produce ends?
So from this here, tau decay, tau goes to n and a pion, let's say.
So you can have tau invisible decay.
No, here what I am focusing is the
Tau to mu to invisible. There is a constraints on it.
tau to mu to invisible.
Yes.
Why you are saying so here in this case?
I think the same thing.
Yeah. I think there is.
So what she's trying to do, she's trying to make the end decay.
But I am not allowing it to go to muon, because I am just looking at the hadronic processes here.
This will be cleaner. In some sense, what she wants to do.
Yeah.
There are limits on it.
Yes.
There are no.
Yes.
Lepton for the heavy neutral lepton?
No, not for heavy neutral electron, just from
Oh, right. Yes. It's there. Lepton and alpha, I think. Yes.
for Alps and everything.
Yes. That is there. Yes, that is possible, but yeah. So actually, this kind of searches can be done in various processes. What the easiest one I just picked up, it's the like hadron in the prompt hadron with a vertex from 2 muon. Even the electron I tried, I went to I went little far in the analysis, but I found the background is a challenge and that needs a different treatment. Okay, so looking at this, since this is long lived, how we find out? So the width, that is the same for all the standard model fermions, with except that we have this V mixing with an HNL. So from that we can extract the C tau, which is around 1.4 and inversely goes square of the V and Mn to the power 5. So if the mass is heavy, then
You have a diagram with Higgs,
diagram for this case,
The Higgs.
with the Higgs.
where the Higgs
With the Higgs also you can have it.
and like virtual Higgs, you mean?
Yeah, virtual Higgs.
Oh, I don't know why we don't do anything like that at Belle II. Is it standard model?
Wait, where is the Higgs? Where is the
Go back, she had Lagrange as the Higgs.
No, where did you put the Higgs?
Somewhere she has written the Lagrange, right?
Yeah.
So this will come from seesaw, right?
Yeah.
So instead of MD, you have a Higgs also there.
This is not standard model Higgs.
Well, it's standard model Higgs. Yeah.
Maybe we can discuss that one. I didn't understand well, so maybe we can discuss that. Yeah.
Yeah, continue.
Yeah, thanks. Okay, so if the mass is very heavy, as you see, then the C tau has to be very short-lived. So it's kind of prompt. So the mass range I am looking for, then it allows that C tau has been to be long-lived given a particular V value. Okay, so yeah.
Is HNL mixes with all the 3 generations democratically?
No. So what I am assuming, since it is coming from tau neutrino, tau lepton decay, so there is the mixing is more with the maximal with the tau neutrino. That's why I am focusing tau decay to find out the mixing of HNL with tau neutrino. Okay. Yes.
Sorry, is that why you were using tau? I thought because of the mass of your heavy neutral lepton.
So we were thinking like various possible. We using tau decay, how far we can go? Like this is the range we can reach using tau. Up to let's say 1.7 GeV, 1.6 GeV. Yes, using tau decay, and that also like something that LSE cannot do because they can't. It's very difficult for them to reach at so low mass. If the mass is low, then the lifetime will be very high. It cannot be measured by their active volume. Okay, so yes, so this is the current. Yeah. So this is the current bound on HNL for 3 different cases. So this is like I have taken from an old paper. Now we have results from CMS and Atlas, but the region I am talking about, it matches with this. So I should have, I mean there is no updated plot, so I just took this plot. There is definitely Atlas and CMS results. Okay, so as you see, the different regions of this mass are being explored by different experiments, and all the experiments provide tighter limit on the En coupling or muon coupling, but the tau n coupling is much weaker in the mass range I am looking at. So that motivates us to study the tau in coupling one, and actually fewer experiments has done these searches like Delphi. Only in the mass range I am looking at, and this is something that FCCEE has been forecasting. But looking at this shape, I think Delphi that they did a prompt analysis, but looking at the shape of this V tau and Mn parameter space, it looked like they did long-lived searches, because in this region, I mean the long-lived searches can give this kind of limit. So just assuming, but what they are forecasting is wonderful. Okay, so yeah, so this is just a future or I mean the unfilled regions are the proposed or future experiments.
What is that line seesaw?
I don't know. Maybe from cosmology.
So BBN is there.
BBN is there. I don't know.
Explains the low scale seesaw.
But what is the constraint there?
No, you can explain the neutron masses for low scale seesaw. Very good. It's not a constraint, it's a theory. Theory man.
No, but
So you
it's ruled out or it's
No, it's as far as I remember, the simplest low scale seesaw can I mean, in order to explain the neutron masses, the simplest low scale seesaw will tell you that v tau and square should be below that in that shape.
Yeah, if the mass is that small, the coupling should be like 10 to the minus 12 or
Mhm.
600.
Yeah, that's why it's small. Yeah, exactly. In order to reproduce the neutron masses. But this is the simplest seesaw. I mean, you can make weird things to make it big so that you can probe these things. So that's a good purpose.
Yeah, please go ahead.
Okay, so the question is, can we directly probe this coupling in the mass range of less than 2 GeV? So this range is not well studied and tau part LHC, given that mass is so small, C tau will be it will be long lived, and it's and then it's if it is low mass, then again high boost, so it will and they have a hard to trigger on the soft tau. So all these limits LHC to look for this mass range, and so the best facility is B factory, Belle or Belle II, even Babar. So because they have small gamma beta around 3, and our for example Belle II or Belle has a displaced vertex radius, it can measure up to 100 centimeter. So and we have larger acceptance than CMS and Atlas for low mass or very high lifetime HNL. Okay, so since we are searching for mass less than the mass of tau, so it can only go through neutral current process. As you see here, and we study the one prong X1, that's the prompt signal, prompt lepton or pion that comes from tau in the displaced vertex, that's muonic. Instead of considering QQ or EE, we are just considering mu plus mu minus, because that gives a better background suppression handle. Okay, so we try to find the mass of the HNL by looking at the kinematic and vertex constraint, given that we have 12 unknowns, neutrino and HNL and the tau, they are the 4 momentum is unknown, and we also have 12 constraints that gives us to reconstruct the mass, but with 2-fold ambiguity. And we actually did this sensitivity estimation in 2020 that was published, that using this constraint we estimated a very negligible background at Belle, and found that the sensitivity will be up to 100 times better than Delphi. That was our estimation, and that motivated me to start the analysis, and that was published last year. And but while doing analysis, I realized that the Belle has lower efficiency than Belle II. That had not been taken into account in the Feno paper, because we have a little bit smaller drift chamber around 80 centimeter and Belle II around 110 centimeter, and we have the Belle has little bit less efficient muon ID. And that I found out while doing the analysis and finding out the discrepancy, and that was the reason that can give lower sensitivity at Belle as compared to Belle II. And I did this analysis at Belle because we have fantastic data set of 1 inverse autobahn around, which includes the data from epsilon 4s, epsilon 5s, 121 inverse femtobahn that Belle had collected, and 89 inverse femtobahn that off resonance 60 MeV below the epsilon 4s and 60 MeV below epsilon 5s. This so the total data set is divided like this, and the cross section is good, E plus E minus to tau plus tau minus around 1 nanobahn, similar to BB bar cross section. That gives us around this many E plus E minus to tau pair. And if you know, we can calculate the branching fraction of tau decaying to HNL. If that depends what is the prompt particle, whether it is just pion or pi 0 or lepton. So depending upon that, we can calculate its branching fraction from the branching fraction of tau going to standard model processes and taking care of this V square. And that gives how many tau. Yeah.
Your name is not there in the author list.
I am a fast author. I am here. I tried to highlight somehow it came here. Sorry about that. That I wanted to highlight.
I thought, I was pretty sure it was there.
Sorry.
Who's El Nayak? There's some other Nayak, not you.
No, that's another Nayak. But I am here in the first.
Yes.
Okay, you'll see. Sorry for that. Okay, so this is the way the analysis started.
That collection of authors is interesting.
Yes.
Some of them are theorists, the previous one.
Yes, we did the analysis with theorists.
They're all theorists.
So I am the only experimentalist, and the previous professor with whom I are working, Abner Safar. So he is experimentalist at the same time. He has more phenomenology paper than experimental paper.
Previous Claudio D.
Yes.
I was in a school.
So there is one more paper coming with him. I have 3 papers, I guess, with him.
Interesting. How did it happen that you were collaborating with
Through previous boss, because I wanted to explore things, and I am little bit more interested to learn more theory. So
this thing can also be obviously applied, even if it is not an unknown particle, it's a standard model particle also. The same techniques can be used. And
Yes.
Can they be used or
like when we measure the lifetime, for example, this is the technique. But but in this case, what is the special is neutrino, HNL. These are missing things. And actually, what I found out this twofold ambiguity by solving this equation. Nowadays, they are using the same procedure to many Pheno paper, and even the Pheno paper that I had published. This is the first time I solved that equation and tried to say that we can actually reconstruct the HNL mass, even though neutrinos are there. Yes, this technique is getting applied. After this it was done first in this case. Okay, so yes, so the analysis method, the channel is E plus E minus to tau plus tau minus. So the tag side tau is important. It's since it's a complicated analysis, I want to handle properly the tag tau so that I can handle the background. So I just try to reconstruct the standard model allowed 1 prong tau decays like all these, and I just avoided these 3 pion and neutrino. Other than this, I considered 1 prong decay. All of them are 1 prong decay. You see one charge track. Okay, and then signal side, I just focus on the heavy neutral lepton that goes to 2 muon in the final state, and look for the mu displaced vertex, and then we restrict the tau going to n pi restrict us to look at mass below 1.63 GeV, around 1.6 GeV below. Yeah. And I start with how the analysis is done. Like the event selection starts with, we require the displaced vertex should be 15 centimeter away from the interaction point. Why I am doing so? Because I want to focus on long-lived HNL, which has small coupling with tau n, and it actually helps to suppress the background that comes from k short lambda, or the particle that interacts with the dense material, even though it's a thin and the silicon detector, but still it's the particle interacting with the material can give you us many different type of background, which is difficult to simulate at least. So in that sense, I consider only the flight distance greater than 15 centimeters. So thus we just focus on our gaseous chamber. And then we require that we should have the CDC, central drift chamber, that's our gaseous detector. We consider only good tracks that should have 20 hits in our CDC, central drift chamber, and that ensures that the quality of track is good. And then we require that there should be no hit on the track that comes from the vertex before the vertex, and that is rejected by applying this R hit minus R displaced vertex should be greater than -2 centimeter. So technical, and this is a summary of event selection that I applied. Like we require that total number of tracks in our event should be 4, 3 coming from the signal side, 1 from the tag side, total 4. And these are some track quality selection, impact parameter selection that's applied for the signal side prompt track and the tag side track, not over the muons that coming from HNL, given that they are long lived. So they are high impact impact parameter, yes. And chi-square, we do a vertex fit at the displaced vertex and look at the chi-square distribution. And so this the vertex fit quality. Yeah, so we bring those two tracks to meet at a particular point. That's a fitter we use called tree fitter that makes them they meet at one point, and we look at the fit quality at that point.
How do you define the fit quality?
So that's chi-square is one of them, and like chi-square of the fit, it should be like greater than something, because around 0 that gives, or 0 or below 0 that gives they are not good fit, something like that. I don't remember exactly.
Because this 10⁵ looks very small.
Yeah, because they are picking around 0. So if I go little bit higher than 0, so then I'll be able to, I can reject. So it should be, actually should be greater than 0. I just make it 10⁻⁵, like very, very, very small. So just by looking at the distribution, I decided it. In principle, it should be greater than 0.
But in chi-square, what do you have actually? Like, you are comparing with something, right?
Yeah.
Chi-square, something expected minus of the chi-square. That's why I'm asking, what is the like, how do you define the chi-square of like?
Yeah, so I have to, sorry, I will look back and tell you, because I just use the fitter and put it. I will go back to the fitter and see that.
Chi-square itself will have no meaning with the absolute value.
Yes,
We need to see the place of the database.
yes, 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 yes. Okay, so the other part is like the displaced vertex, the two muons that comes from the vertex should be in a co-limited way, not like it's boosted, so it should have a theta not kind of back to back but small theta. To ensure that, we require that the angle between those two muons should be greater than 0.5, that selects a boosted object and suppress the cosmic background. For the cosmic, it should be 180 cos 01. So -1. Okay. So, and then we require that to suppress background and to consider only pion, we applied some selection over lepton ID selection, that so it's not a lepton, and we don't apply any particle ID on the tag side, so that we can take all standard model processes. And then we some muon likelihood cut we applied for the displaced vertex tracks, and the most important, we require the mass of the pi and the displaced vertex invariant mass would be below 1.776 GeV, to ensure that the process is coming from the tau decay, not something else. Okay, so this is the analysis. So given that K sort is long lived, neutral particle, so it can produce a displaced vertex similar to mu, given that muon is misidentified as a pion or pion as a muon, sorry. So we tried to explore, we excluded this K-short mass region, and while excluding the K-short mass region, we looked at the HNL signal, like low mass signal and high mass signal, and how they distribute in the invariant dipion invariant mass. So for the low HNL mass, they mostly distribute the lower side of this K-short rejection mass range, and heavy neutral lepton that picks around the high mass region. So the low mass HNL distribute differently than high mass HNL. Hence, we define two signal regions targeting low HNL and high mass HNL. And as you see that in the low signal region, there is some possibility that high mass sample with loose events. However, that for the case of 1.6 GeV HNL, then the more than 90%, 95% of the sample are in this region. So we don't care.
Green line, which is signal 300.
Yeah, we done 300.
Like a peak, right?
This is not a big, yeah. This actually we can go beyond that. Just for the high mass HNL.
Yeah,
okay.
It doesn't show any like.
Maybe in the higher mass region. I just wanted to show this region how I am separating things. Yes, so they will pick behind this region, given that mass is high 1.6 and 1, I am just focusing in this region to focus how I am defining my regions and how much signal can we lose if we apply such cut. That's the idea here. Okay, so after doing all this analysis, this is what Monte Carlo predicted, that we will expect 0.4 events in the high mass region and 0.8 events in the low mass region. Yeah.
Previous slide, sorry. This peak, that is K-short peak.
K-short peak, K-short peak.
This K-short peak doesn't look symmetry, right?
Yeah, so with muon misidentified as a pion, so it's in our analysis it's not symmetric, but we just for that analysis, in that particular analysis, we just make like use the pion mass hypothesis for the case of muon. So it's
K-short decays to pion.
not K-short, displaced vertex. Okay, so muon with pion mass hypothesis and look at the inverse mass hypothesis. Yes, little bit asymmetric. Yes, because originally in the analysis, that is what will happen. That is the possibility. Not like yeah, everything how it will look if it is misidentified. Even the resolution will definitely be poor. Okay, so this is what Monte Carlo predicts. It's quite clean. And the possible background, so we use 5 times simulated data as compared to the real data. So if I take 5 times of that, so what we expect, like 2 events in the heavy region and 4 events in the light region, light mass region. So I looked at what are those background types. This is the background, like tau can go to pi kk with a neutrino, where pion decay in flight to muon, for example, and kaon can decay in flight to muon, and they like somehow cross each other and contribute to the background. And similarly pi k short, where one pion goes to muon and one pion from the k short can decay to muon. And then from the k long, that's L pi, for example, one L is there and another pion can get misidentified as a muon and can contribute to the displaced vertex. So these are the possible backgrounds when we use the 5 times more statistics. This is only with 5 times more statistics, we see only 6 events, and when we normalize that, it's very small. So to validate our prediction, we we define various control region and validation region, which will differ from signal region by using just the particle ID cut. So these are our validation region, like we look at the displaced vertex with same sign muon. We should not see that kind of accidental crossing. So that we see that there is almost 0 events that we saw in such case. And then another control region where we use like mu pi displaced vertex and look at the agreement between data and Monte Carlo. That gives good agreement. And similarly K-short exclusion region and inclusion region. So and we see that there is kind of kind of in the inclusion region and any difference that we take as systematic uncertainty.
So in your background, you always have tau, right?
Yes, no. In our background, there are 4 taus. One that is coming here in the low heavy mass region only from tau. In the low mass region, there are 2 tau and that 2 coming from QQ bar, like heterogeneous process.
I'm saying that why don't you have anything from like B decays or something?
B decays, that's B decay. So generally, B decay what? It said B decay will contribute like very negligible.
Yeah, that's all. You have simulated and you have found it negative.
Yes. I have that in the table, but generally the QQ bar background come from like low mass cases like UDS.
You are using the second tau as a tag.
That doesn't give the that can give, but no, we define 2 hemisphere, one signal side and tag side, so there is no accidental crossing.
That's what I'm saying. Because
Yeah.
you do that, many of the backgrounds drop off.
Yes. There is no possibility that some of the background from tag side will come to signals because we define them in 2 hemisphere. Sorry. Okay, so this is the chord flow table that I just thought of putting, that the background that can come from different processes, and after applying step by step, applying all these chords. That may be meaningless for some of you, it's boring, but I thought just completeness to put it. And we see that the background that can come from EE or mu or 4 lepton or EEQQ, they give like zero contribution, and this is done with 5 times statistics. And the background that comes is from tau and QQ bar at the end. So, yeah.
And then your last
These are the signal cases, like how much efficiency we are losing after applying H cut.
so in this are one means what? Like you have 0 for signal.
Which one?
Yeah, last.
This one, yeah. So, this is the high mass signal, and this cut that we apply is for low mass signal. So, that's expected that it would be 0. Yes, below that pi invariant mass cut. No, that's one case, that is pi invariant mass cut drop down it here, but another cut we apply for the signal region low, that there will not be any event in the very high signal region, given that this is targeting low mass HNL. That based upon simulation we applied another cut, that low mass HNL cannot peak in the very high M plus A minus region.
So we have two given in the final step, right?
Yes.
But your chart is written m pi displacement.
This pi, that's we say like using pi and mass hypothesis. This one, this what I'm saying here, just this cut. We are separating our signal region. You can say it like mu invariant mass, but without having neutrino. If we just that is kind of mu when you say it's true mu. That means there is no such, we will not see such kind of things. That's why. That when we see such peak, that means it's pion. Muon is misidentified as pion. Yeah, maybe I can discuss later. Yes. Okay. Okay, so as I said, this the HNL mass reconstruction is done, and we end up with a quadratic equation. And one of the, if I look at the square root argument, I found that in the signal case they are picking around 0. For background they can go away from 0. This is kind of technical cut, not has any meaning, physical meaning of the square root argument. Yeah, so I select signal that has low S value, and by using S less than 0.4, that way we reject some of the backgrounds here. And if the S is less than 0, and where only signal is there, no background, so I make it S should be equal to 0, so that I don't lose any signal efficiency. Okay, so after this I make this is my final result. I just put the simulated signal of mass 0.6 GeV and how the distribution look like. And these are two regions, one is a low signal region and other is a high signal region. And when we unfolded the data, yeah, so when we unfolded it, we look at the mass M plus A minus region, and we see only one high mass signal picking having here, and there are two here that get excluded. That's with the low signal region hypothesis, and that get excluded in the signal region light cut. That's M plus A minus. That means if we are targeting low mass HNL, they should not be picking here. So what is picking here is just the background, not the signal. Signal, we restrict that the low mass signal cannot go up to here. Here data is points. Triangles are tau background and square is q bar background. And so what we end up seeing is one event in the high signal mass region and this low signal mass region, these two get vetoed, rejected. Yeah, so this is in agreement with our background expectation, and then we estimate our efficiency we use the model prediction and the efficiency to determine how many S signal events that we expect. And we obtain the signal efficiency for SRH and SRL as a function of tau and coupling. And looked at the systematic uncertainty. The background estimation is the largest source of uncertainty. Others are negligible compared to the background source coming from the branching fraction, decay modeling, luminosity, cross section, all these things. And all these systematic uncertainty are handled in our nuisance parameter. And at the end, this is the limit that we got at the 95% confidence level exclusion limit, and we have used a new analysis technique. This is the Babar limit. I didn't understand this limit, it doesn't close anywhere. and what it says, it's from a recoil mass, it's a prompt analysis, not a displaced analysis. And this is the region where analysis was sensitive, but the author of the referee of the journal asked to put the charm and WS66 reinterpretation. It's not a real data, I mean analysis, but reinterpretation. If we put it, then we are nowhere. But the thing is, it's we are using displaced vertex technique to exclude this parameter space.
This charm result looks very strong. Right?
Very strong, but it's not a dedicated analysis, it's a reinterpretation.
But I don't know anything on charm experiment.
Yes, it's a fixed target experiment, as I know.
How much data they like?
That I do not know, and it's not a real analysis, just a reinterpretation. We just put it from the.
I'm just asking like that one thing for because they want like clean environment and everything, right?
Yes.
But charm experiment is giving this kind of very strong linkage. It's just from interpretation, reinterpretation. But looks like very strong, right? Compared to actual analysis.
Yes.
I think it's too strong. I mean, it's just it's like 2 orders. So let's look at the bottom. It's like for IISc, for IISc, it's like 2 to 3 orders of magnitude stronger. So that means the lifetime that they are probing is also b square, right? So that is proportional to 3 orders of magnitude stronger. So it doesn't seem right. Yeah, it just doesn't
So
seem
you will
right.
not be able to reach there, right? Even with all the data.
No, not possible. I have the limit that I put, you see here, and the beginning of the analysis. That's what we expect with all the data. Go up to -5.
But who actually reinterpreted that data? You got it from some paper or?
Yes. So since since the journal referee asked, we just quickly put it. Yeah. Fixed term. Yes.
All of their bounds are extremely strong. So you end up getting a region between those bounds and the direct bounds where you grow. So I don't know why they are so strong, but for different displaced vertex
Yes, I also see this.
they are very strong.
So they have like many particle on target, like I don't know.
No, they have nucleons. So I mean,
But I know that even in these say the dark on white paper, so they explicitly say that we should not use things of these things because we don't know the systematics. So they have once asked that how many people have done have probably passed away, the floppy disk is lost, we don't know how to read the data. So they explicitly say in the white paper that we should not trust these things too much. The reinterpretation, systematics is not mentioned, things like that.
there's this 3 chart, Porsche and E100
Those
something.
are about some knowledge experiments.
Sir, one more question, like this displaced vertex. So what is the maximum length you consider?
Sir, so CDC radius up to 100. No, for this is Belle analysis, so 85 centimeter.
For this one?
Yes.
If it's still that far away, so will the tracks hit 20 cells?
Sorry.
You had a criteria, right? That the
Muon.
Muon.
Muon, we have a different detector. We just want to focus on how far we can probe the displaced vertex.
No, but you had a criteria
Uh-huh.
that it has to hit 20 cells in the CDC.
Track, not the
Yes,
vertex.
but the tracks are the muon tracks, right?
That's a good question actually. If that is, let me think, if no, it should be greater than 20, understand. So if suppose we reach at the boundary, that's like 50 hits. So what is the problem? The lower limit is 20.
No, I'm saying if the displaced vertex
Yes.
at the boundary,
At the boundary,
the muons are there only after the displaced vertex, right?
yes.
So how are the muons hitting 20 cells?
20, they are not starting, they are not coming from the CDC itself, but the boundary of CDC that gets accepted in our court itself. When we say that CDC hits should be greater than 20, that means at least 20, that means the counts are the inside inner radius. So when it gets counted, so it's the inner cells hit.
But inside, let's say a particle is sitting at the edge.
at the edge, but inner cell heat we say that should be greater than 20.
But inner cell there is no heat, right? It's a neutral particle. The neutrino is
No,
a
no,
neutral
it doesn't need to have heats. Like if we require, what this says that we don't consider like particles that has like low momentum that only calls inside CDC, but at least the particle reaches inside our SBD, but at least it reaches the gaseous chamber CDC and beyond that. What we are asking, I understand, but that way like what 20 hits means that inner track hits.
Yeah, but okay, I'll ask.
Okay, so I understand your point, but this is, okay, let me think about that a little bit more and get back to you. Okay. So when I say 80 centimeter, that I say in the R direction, not in the G direction. Yeah. Okay, so I'll talk later that. Okay, so then I'll start. So already it's going to be 1 hour. I don't know how I'll complete this. But this is charm physics that I wanted to talk about, that another route towards new physics that I am doing here in IISc. Before I go to CP violation, let me remind that there are 3 types of CP violation. One in CP violation in decay, just we measure the decay rate of the particle to going to a final state, it's in CP conjugate. And then another one is CP violation in mixing, just we look at the oscillation probability for D0 to D0 and D0 to D0 bar. If it is this probability difference is not equal to 0, then it's due to mixing only. And there is indirect CP violation, that's mixing induced, like there is a case like D0 can go to the final state, or D0 can oscillate with D0 bar and D0 bar goes to the final state. That's kind of mixing induced CP violation that occurs in the neutral particles, but CP violation in decay occurs in the charged particle where there is no mixing. So why charm? In the charm sector, the standard model contribution are very small in CP violation as well as in the FCNC, flavor changing neutral current processes, and it offers large window to search for new physics. The CP asymmetry expected in standard model is below 10 to the power minus 3 and mixing below 10 to the power minus 2, and it's an unique probe for op type quark sector to look for new physics. So since I am doing CP violation in decay, so to search for CP violation in decay we need at least 2 amplitude, because if we consider only 1 amplitude and even though it's complex and make it the square of the amplitude, both will become real and we cannot measure the phase difference. So to measure the phase difference we need at least 2 amplitudes to the same final state, and we can measure the phase difference. So since I said 2 interfering amplitudes, that means one can be from tree diagram and the other can be from penguin diagram. Tree doesn't contain like that much CP information, where in the new physics information, and penguin contains the new physics information, so that would be good to explore new physics possibility. So this is the in case in the CP violation in D decay has already been observed by LSCB. They didn't directly observe through one channel, but delta ACP they measured, which is mostly the CP violation that comes from KK process, given that single Cabibbo suppressed. And recently LSCB found strong evidence of CP violation in direct decay using D0 to pi. So here they didn't actually measure the ACP direct CP ACP in D2 pi, but they measured ACP in D2 KK and combined with the asymmetry delta ACP to extract this direct CP asymmetry in D0 to pi. So there is no direct way to measure direct CP violation in D0 system, because they can oscillate and become D0 bar. So the only possibility is D plus system, charged D system, where only type of CP violation in direct CP violation is possible through charged particle. So relatively easy to measure, only we need to measure the branching fraction, and if the branching fraction of the charged conjugate decay is not similar, that means CP violation. So I did this search using, so to do this search we pick up a decay where the leading tree diagram is not overwhelmingly dominant, like we should consider the single Cabibbo suppressed decay, as in this case like 3 possibilities we can draw. So, we need at least 2 diagram for the interference here, 3 diagram, one is tree, one is loop and another is this annihilation diagram. So, this is single Cabibbo suppressed as you see in VUS. That in the single Cabibbo suppressed decay we can explore this direct CP violation, and similarly for the D sub S to K short pi pi, which is again a single Cabibbo suppressed decay. So, we use these 2 channels to measure CP violation, and we use control channel that are mostly Cabibbo favored decays, like D plus goes to K short pi pi 0 or D sub S to K short K pi 0. They are mostly dominated by Cabibbo favored diagram, although there is doubly Cabibbo suppressed contribution is there, but but that is very small. Okay, so how we measure this CP violation? CP violation, CP asymmetry results from the difference in decay rates between the matter and its counter antimatter part decays. So, to measure this ACP in K short S pi 0, it is more straightforward to measure the number of decays of each type to a common using a common data set. That we say as raw asymmetry by measuring the number of signal D plus going to its final state and CP conjugate part going to its final state. And raw asymmetry, it not only contains CP asymmetry, but there are other asymmetries. So, which includes others, as I said, which includes other source of asymmetries. So, this raw asymmetry is a combination of all these. So, we are looking after the CP asymmetry, and then there is production asymmetry, that the number of D plus and D minus that gets produced might be different, and then the detection asymmetry of the pion or the charge track and the CP violation in K short. We have to take into account all these things to extract ACP. So, the easiest way is to measure delta ACP, because we know in the control mode, which is mostly Cabibbo favored, no CP violation. So, if we just subtract the raw asymmetry of the signal mode from the control mode, we can cancel out all these 3 things. So, just what we will see is delta ACP, which is the CP that we measure that we get from the single Cabibbo suppressed mode. That is the idea. And if you look at the branching fraction of this signal, so which has much higher branching fraction than the D plus to K short K, which has already been measured. I mean, these 2 body decays has already been measured, but these things has never been such precisely measured, given the they have higher branching fraction. So, for these channels only Clio had provided some limit on the D sub S plus channel and D plus channel, whereas base 3 provided limit on the D plus going to K short K pi 0, but there is no measurement yet for D sub S to K short pi 0. So, yeah, so we try to do this measurement using Belle II Monte Carlo and use untagged approach. That means we do not identify what is the the accompanying pion that comes with D from D star. We just focus on D, nothing else. So, it's different from the E plus E minus to BB bar that gets produced at epsilon 4s in our machine. It's when we look at charm, it comes with fragmentation. So, we have 2 charm hadrons along with fragmentation. So, this is some general selection criteria that I used to select our track and particles, and we optimize our selection based upon figure of merit. For example, momentum of D, we require the momentum of D to be very high. That means we want the D that comes from B which has low momentum, we want to reject that. So, we did so using figure of merit, and we looked at the flight distance significance, and we applied certain cuts, because the D plus has a lifetime or D sub S plus has a lifetime, whereas background mostly has 0 lifetime. That way we reject, and certain other criteria we used, and this is how the distribution look like after we apply all the cuts for all the modes. And before applying the cut, this is how the distribution was looking like. Look at this sub S to K short pi 0. So, they had a huge background, we could not see the signal. Now, after applying these cuts, we drop the background like 99% of the time, and we can see the signal peak at least here. And to determine the raw asymmetry, we fit each of the distribution, and using certain signal PDF where we use mostly double Gaussian and bifurcated Gaussian and a crystal ball, given that there is pi 0 in the final state. Background is mostly a second order polynomial. There is some picking shape which we fix using Gaussian distribution, and we did a one dimensional extended maximum likelihood fit to extract, and similar procedure is done for the other two channels for the D sub S channel. And this is what we obtain, the yields and the asymmetry. This is raw asymmetry, since given that it is Monte Carlo. So, what we should look at the precision uncertainty. So, if I compare this uncertainty over the previous measurements, I see that I am expecting in data, I am expecting to see an order of magnitude improvement over the previous measurements. So, that is very interesting. At least we can measure this D sub S to K sub pi 0, and we can improve the precision by an order of magnitude, and hopefully we will see CP violation in this channel. So, the analysis is currently ongoing, and we are also using BDT based approach to reject the background even more, and look at the picking background that we see. That is a small picking background that is picking in the signal D region. We are understanding that, and next we will conduct the Toy Monte Carlo study to assess the fit quality, and the dominant systematic uncertainty comes from the fit model and the kinematic reweighting between the signal channel and the control channel, looking at the momentum distribution of D, for example, or the polar angle. And then once we understand that, we will unblind the data to extract ACP. And last part, I will go quickly about the char mixing, what I am doing right now. I started doing. So, the char mixing is suppressed in the char standard model. It is both Jim suppressed, it is decay suppressed, and there is MB over M2 that is in the loop, which is very small. So, long distance contribution are significant, making this prediction challenging. So, this is small in the standard model. So, it is a potential, it has potential to search for new physics. As you see here, the mixing is very small in the D0 bar system. We need a log scale to see it. So, it offers sensitivity to non-standard model processes that can increase the oscillation rate or induce CP violation effects. Okay, so this is the phenomenology of D0 mixing, how we express the mass eigenstate as a combination of Flavor eigenstate, and if we do the time evolution, and we end up seeing this is the time dependent decay rate to a CP eigenstate, which is we write it as YCP, which depends upon the X and Y, this mixing parameter, and also CP violation in mixing, and through this measurement of this Q over P, which in case of no CP violation should be 1. If there is CP violation, that is due to mixing, it should be not equal to 1. And also it has a contribution from direct decay, and the phase factor, if there is CP violation, will not be equal to 0. So, yeah, so the lifetime for decay to CP eigenstate can be expressed like this, and it can be experimentally measured by measuring the lifetime of CP eigenstate to the Flavor eigenstate. And this is the world average that has been measured, and this is mostly dominated, the precision dominated by LSCB recently in 2019. In 2020, I provided the K short omega result, which is the CP odd mode that has not been done by other experiments. So, this is the current world average of YCP. So, and if we look at the world average of Y, so if there is no CP violation in mixing, then YCP should be equal to Y. If there is CP violation, then YCP will be different from Y. But given that the precision is not so good, we can't say we can trust this central value. So it's important that we improve the precision for both YCP and Y to say something about CP violation in mixing. And since a time dependent CP violation, and we measure it experimentally by tagging the D from the D star decay, and we know the flavor of D0 or D0 bar from the pion that comes out from the D star plus, and then we calculate the proper time, and the way we calculate the usual way, and then we extract the fit the decay time distribution to extract the lifetime and measure YCP. So this is just forecasting how I was doing at Belle. So first we identify K short, then omega resonance peak within this 3 sigma region, then use that to make a D, and fit the D mass and delta m, that is the D star mass minus D mass, and then make a 2D fit to extract the purity in the 3 sigma region, and this is necessary for the lifetime fit, and do the lifetime fit by having the weight for signal events from the previous fit and the signal resolution function, then the background decay distribution. And once we do the fit, this is what I extracted for k short omega and k pi, and this is the YCP value that I had provided. Since that was done in Belle for both the YCP plus CP even and CP odd case, at Belle 2 if we just scale the luminosity, this is what we expect at 50 inverse or to 1 just by luminosity scaling. But we know that there are a lot of improvement with the Belle 2 detector and a lot of modern techniques coming in. So we expect we to achieve far beyond what is I am just forecasting based upon the luminosity scaling. So this shows that we should measure this channel very precisely at Belle 2. Yeah. Given that Belle 2 has this merits to make these precision measurements. Okay, so this I started with a bachelor student. So yeah, so if he did this analysis and measured the lifetime, and if I compare the lifetime that was measured by Belle 2 with 72 inverse femto1, again this was world's most precise measurement, and so he measured like with 500 inverse femto1 statistics, and he saw much precise result than what was already done with smaller statistics at Belle 2. So this motivates us to do such mixing analysis that depends upon the lifetime with higher statistics and with higher precision, so we can uncover new physics in charm mixing. So that's all. Sorry.
Questions?
Can you show like the charm?
Which one?
The charm is
Okay, HNL. Yes. I should have looked that, but I'll go through it and maybe we can discuss it. Hmm? So I want my paper to be published. I didn't want to argue that this is not a measurement. So just
proton on target from 10 to the power 18, so it's not very far from sheep experiment, right? Yes. We can expect 10 to the power 20. Yes. And this 400 GeV proton and 10 to the power 18 proton on target. So maybe it's possible. Okay, it's old experiment, but they have 10 to the power 18 protons.
But for when sheep plots their sensitivity, do they use this charm? They will not use it.
So if they plot this kind of thing, if there is a signal, how they will find it? They are just excluding this region based upon this. They cannot say if there is any signal, right?
Yeah, they have not found anything.
If they didn't found anything for suppose some higher range and using higher statistics they scale it down, that means we don't know if they can see anything if they don't do the real analysis.
No, what I'm trying to say is that the number of protons on target was 10 to the power 18.
Yes.
For sheep it was 10 to the power 20.
Yes.
So although it's some very old experiment, the sensitivity should not be like very weak.
Yes, so that part I understand. It's like phenomenological prediction, like we can achieve up to this limit, but we cannot say like if there is a signal within that region. Yeah. If we don't study, we will not know, and with that way we can exclude this region.
What is the argonic purity? That is the new experiment. Argonic. What is the purity? This is not for now. One can change.
No, it's a field one, so that means it's a measured.
No, argonium. What is the purity? Proton target. That's also fixed target.
Hmm.
That can be easy check whether this.
Mhm.
And probably energy is small.
Yeah, no, that's fine. But I think this POT, I mean, just the number that. Yeah, so then obviously this charm thing is something one.
No, but energy.
No, energy is obviously different because it's going to lower masses. So with 10 power 20 or DG 10 power minus 3, 10 power 18 energy.
No, another thing is the shielding and other things, right? Maybe it's
Yeah, seems to be right.
3 G. And this is for 400 G. Charm.
3GP what? Photon? Sorry, photon is this.
Carbon is 3G. No, carbon is earlier, right? 3G is earlier. Carbon is
Maybe we can
earlier.
discuss this.
Yeah.
So let's thank Minakshi.
Okay.
Thank you.
Thank you all.